I don't know how many people of you know this, but apparently we are the longest running SIGGRAPH BOF. I didn't know this, so give yourself a hand. I didn't know this till about a couple days ago. Somebody looked at some statistics. We've been running since 1996, and apparently we're the longest running. We hold a record, longest running. So I owe all of you a big thank you. Okay, I'm Teresa Marie Ryan. We're going to have a lot of presenters today, and here, my introduction, that was the introduction. So Caesium is going to be up here. Mike is up here. Mike is in the house. We got Web3D. That's going to be Nick. And Esri, we got you guys here. And we got Uber here. So we're ready. All right. Okay, so without further ado, Caesium is here. I don't kill myself.
Thanks. Hi, everyone. My name is Omar. I work as a graphics programmer at Caesium. I've been there for about a year now, and a lot has happened in that year that I'm excited to share here. So these are kind of like the three highlights I want to talk about today. So 3D tiles, the format we created to make it easier to stream massive 3D data, is officially an OGC community standard. Caesium is spun out as an independent company, and we've been working on curating a lot of publicly available data sets by partnering with data providers such as Vricon. So this first big piece of news that 3D tiles is now an OGC community standard happened back in February. I'm pretty excited about this because it means we're kind of moving towards a world where it's much easier to share and work with massive amounts of 3D geospatial data. So if you're not familiar with 3D tiles, the idea is that regardless of where your data comes from, whether it's captured from like the real world, like photogrammetry or LiDAR, or if it's like massive like architecture design models, you can put that all into this one open format. And once it's there, it makes it really easy to stream because you can load in just the pieces you need for any given view. So for example, here is, this is a high-resolution photogrammetry data set of Melbourne, Australia. It's captured by Aerometrics. The full data set is like 11 gigabytes. So if I wanted to download this on my office Wi-Fi, it might take like an hour. And then I'd have to find like some kind of desktop viewer and make sure I had enough RAM to load the whole thing. But with 3D tiles, just this view takes about like 30 megabytes to load at this highest resolution. So it goes from like an hour to just look at to just a few seconds. And because it can be streamed over the web, that can be just a link that you sent to someone that they can look at on their phone even. So 3D tiles is, it's great for making it easier to share, but it's also made from the ground up to be efficient at rendering. So that makes it really good for any sort of interactive analysis. So if you're running your apps in real time, or you're trying to add heterogeneous data sets on top of that at runtime interactively as well. So an example of that, this is the same data set again. On top is a GeoJSON data set. I got this from like a public Australian government website of all the roads. So like orange is like main arterial roads. I think green is like the public transit lines. So I can do this kind of dynamic fusion where I can say, let's say I was only concerned about seeing the roads. I don't necessarily care about what type of road it is. So I can sort of do this intersection query at runtime to hide everything else and just show the roads. And I could have done the opposite as well if I just wanted to see the buildings. And this can be done without having to like reprocess the data set or anything. So you can just essentially be dragging and dropping in these dynamic data sets. So the second big piece of news, and this is kind of hot off the press, Caesium spun out as an independent company. This is just a few weeks ago. So for the past 7 years, Caesium has been part of the parent company, Untitled Graphics. And the initial use case for Caesium was you would do your kind of satellite tracking analysis with the desktop tools, but there wasn't any way to share your 3D visualization on the web. So that was what Caesium initially was created for, and it's since grown into a tool for all kinds of different industries. So while Caesium is most commonly known for the open source Caesium.js library, we've also been pouring a lot of work into the Caesium platform, where you can either find data sets or upload and host your own. So for example, right now, this is where most Caesium apps get their global satellite imagery and terrain data. And what's really important for us is we build this commercial platform on top of open standards like the 3D tiles. And that way, all the work we do as the platform grows can fund these tools that everyone can benefit from and use. So here's kind of how it all fits in. So on the top left, you have sort of the Caesium platform, like I said, where you can either you can put your data, whether it comes from real-world captures or sort of synthetic design models. And since that relies on all of these open source tools like Caesium.js, as the platform grows and develops, those can continue to grow and improve as well. And this isn't just Caesium.js, even though that's the most popular, but we also have like a lot of smaller open source tools like the GLTF pipeline and OBJ to GLTF command line tools that are all, they're all part of our work, and so those can continue to be funded and developed by our work in the platform. And then there's the broader ecosystem where, once you have your data sort of tiled and fused on Caesium, you can take that out. So you don't even have to visualize it using Caesium.js. You can put it in any other client that can ingest this open standard 3D tiles. And that, I think, is really important because then as data becomes easier to share and fuse, and users can stream the data they need on demand without having to license like the whole data set, this data becomes a lot more accessible, a lot more affordable for all kinds of new use cases. So that's something I'm personally very excited to see. So kind of as an example of data becoming more accessible here, we've partnered with Vricon to make their photogrammetry data sets publicly available on the Caesium platform. So Vricon collects high-resolution photogrammetry data of a lot of places that are really hard to capture in the world. So I have a demo here I can show. So this one, and correct me if I'm wrong, but I'm fairly certain this is the first publicly available data set of the pyramids of Giza. And this is kind of a big deal for me because I grew up around there, and I remember like always looking at online platforms and never seeing like, the US always had these great 3D models, but then Egypt was always flat. So here, I can kind of see that you can do any kind of analysis like, measure some distances or angles. Here, you can also, this is all built with Caesium.js. Let's say you had some sort of drone analysis where you want to see this visibility from this drone. So here's kind of what it sees, and here's what occluding its view at any particular point. But this is what's really valuable about this is when you can combine these data sets with your own data in your analysis. So if we jump over here to Damascus in Syria, to show this example, we partnered with data from Spatial Networks. So Spatial Networks has local survey data. So they have people in these countries who walk around, either like they look at records or they just actually talk to people door to door, collect like local information about anything from like the locations of security cameras around to like the prices of eggs in various different shops. So here, one data set we have here is a vector data set of where all the worship sites are. So where all the mosques and churches are. So you can kind of see highlighted here. And this is the same thing I did earlier with the roads with the GeoJSON. So this, if I click on it, I can see it's actually a church, and it's also used for funerals, and I can see what the neighborhood name and everything is. And this is kind of just scratching the surface, so I can do things like I can filter by any sort of arbitrary query. So if I want to sort of color them by type, so here I can see all the green are the mosques and all the blue are the churches, so you can kind of at a glance see their proximity. And the cool thing was that this was like a separate data set that we got like a day before demoing this at Geo, and so I was just able to drop it in and see that sort of filtering pretty quickly. And as they update these data sets, I don't have to reprocess the giant mesh either. I can keep updating that over time. So the data itself is available on Caesium platform, and you can actually try it out. There's 6 cities. Cairo is one of them. And the demo, there's a live version of the demo as well as an open source version that doesn't have like the analytics tools that you can play with, and that shows you a lot of how to set up like the drone flights I did there, and how to combine it with your own vector data sets as well. Give it a second for people to take pictures of that. Okay. Yeah, so looking forward, I feel like there's a lot of exciting things coming down the pipeline. One thing that I'm very excited to see is more clients supporting 3D tiles. So right now, most people will use Caesium.js to render 3D tiles, but we're seeing people implementing it in Unity and Unreal Engine, where I think it'll unlock a lot of really interesting applications, especially building on those rendering pipelines. And also the big one is supporting being able to tile more formats. So right now, you can tile point clouds, CAD, architecture, things like that. But having a vector format in 3D tiles would be very useful, because like I showed demos of roads on top of the cities, but then if you want to have like a global road layer, that's something that's still a vector format in 3D tiles would enable that, which currently would be difficult. Being able to extract metadata from the data that comes in. So right now for city GML, for example, if you have a lot of buildings, the buildings can come with metadata like their age or their height, addresses, and with Caesium, with the platform, you can extract those and then filter those at runtime. But with GLTF and with 3D models in general, there isn't a standard way of sort of embedding metadata that we can extract. So kind of coming up with a more flexible pipeline to allow people to embed metadata and then extract that and query that at runtime. And finally, a lot of the analytics tools you kind of saw earlier are not currently available on the platform, but that's something we want to put as well to make it more accessible to be able to do these kinds of analyses. So these would be like the measurement tools that I showed here if you want to do distances or areas, but also volume as well as the visibility analysis, whether it's a drone or any kind of autonomous vehicle. So that's all I had. And if you want to see what's coming up, make sure to follow our Twitter or just email me if you're doing anything cool with 3D tiles. I'd love to talk about them. Thanks.
Can you take one or two questions?
Yeah, you don't have a question? Yeah.
So I'm a pretend cartographer. I'm just in the process of learning this for my professional career. So you talk about your 3D tile standard, how it should become the OCD standard. What does the major companies like Google use for their 3D stuff, and how does that compare to your standard?
That's a good question. So I'll probably let someone from Google answer exactly how they use, because I think, as far as I'm aware, it's not open. So you use, there is a KML format which you can export from Google Earth and as well as import. So you can take that KML Collada format and put it into 3D tiles as the buildings. Whereas for example, for the photogrammetry data in Google Earth, I don't know that that's open. So I guess that's kind of the value here, is that because it's an open standard. So right now, Caesium.js is maybe the main client, but then more tools and ecosystem going around that makes it easy for your data not to kind of be locked into any one format. Thank you.
We do have ESRI here, so they can say something if they want to say. When they're ready, you want to answer?
Maybe if I could comment on that. If this is
I saw him ready to comment.
So the question was, what does the major companies do? So along with 3D tiles, there's also another open format called i3s, which is also adapted by OGC. Actually, it was the first one to be adapted for streaming massive amounts of mesh and 3D content data. But the concept, having this bounding volume hierarchy and being able to stream massive amounts of content from client-server technology is available, and there are different formats. It's just that, like JPEG and PNG and TIFF, those are all different formats. They all capture image, right? So That's what I would say. I would put it like that, that there are different formats that would allow you to stream this map.
Good job. Mike, you're up. I'm going to let Mike introduce himself. He's with this Monterey place, Monterey Bay, something. I have a sense of humor, everybody.
Yeah, so my name is Mike Mccann. I'm a software engineer at the Monterey Bay Aquarium Research Institute in Monterey, California. And that's not the first presentation I wanted to show. It was this one. So I'm not sure if I was at the 1996 first meeting of the Cartographic, but I think I was 3 years later. And this is always a great event at SIGGRAPH. It's a chance for my field of oceanographic research and dealing with a lot of the data that we collect beneath the layers of these wonderful layered approached systems for visualizing the Earth, things like Google Earth or Caesium. And what we really care about in the ocean is the data underneath that, underneath the surface of the ocean, and even underneath the bottom of the ocean and the geology of the Earth. So we start with the coordinate system, and our fundamental problem that we presented 20 years ago at a Cartographic was we have this latitude, longitude, elevation coordinate system, but all the computer graphics is just Cartesian XYZ. So how do we convert between the two? And so I'm going to tell the story about how we can do that now in a standards-based way that enables us to do the scientific work that we need to do. So I'm not going to describe in detail this coordinate system here, just a little bit of eye candy here. But what with the result of that first meeting 20 years ago at a Cartographic is we added a component to an international standard for 3D graphics on the web. And it's called the Geospatial Component. Its desire was to make it easy to use geographic data in the X3D standard. So typically we provide geocontent and latitude, longitude, elevation from GPS, and we wanted to translate those data easily to XYZ coordinates used by computer graphic systems. There's lots of other issues, numerical precision that needs to be dealt with when you pass the data to a GPU. And then the navigation inferences. If you're going to walk or fly through some sort of terrain, there's this concept of what is the up vector. And the globe is, if you're XYZ, which way is up, you have to convert that. So this geospatial component deals with these issues. And the end result is it handles all of the transformations and precision calculations to easily work with geographic data in modern computer graphic systems. Again, there's a list of nodes here that we can add to an X3D scene. And the result of that is, I'm going to show from one of our colleagues at Harvard University has created his website, and his name is Andreas Plesch, and he's a structural geologist who studies earthquakes, and he works for the Southern California Earthquake Center. That's my stuff I'm going to show later. It's just my computer's switching to the PowerPoint. And he's built his own website. And he's a geologist. He's not a graphics expert. He's pretty smart and pretty capable. But a domain expert can compose a web page of these components, which he's done to visualize these earthquakes. There's a lot of detail here in the graphic here, but it's the actual earthquake that was just a month or so ago that was in the news. And he's visualizing each of the earthquakes directly from the USGS website, directly streaming into his website to show the data in 3D. So and he's able to bring in the known faults and show them with the locations of the earthquakes. It's a combination of the X3D standard plus HTML5. The 3D content, he's using a JavaScript plugin called X3DOM. It's an open source plugin to render the X3D, and then just using standard web development technology to build his own website to visualize these earthquakes the way he wants to visualize them. And there's different features. This is all navigable. You can spin it around and look in and zoom in on the fault lines and bring up the metadata on each of the earthquakes. Everything's accurately georegistered so that the sub-meter scale accuracy is maintained. And it's just a snippet of what the web page looks like. You can view source on it. You can see all the nodes. They look just like HTML nodes, a little bit of JavaScript to kind of link things together. So this is a way to compose data visualizations that are accessible and meet the needs of the domain scientists to visualize features underneath these layers that we see otherwise. Here's another visualization that he's created. It's a volume visualization of the sound velocity structure in a plane from here to the epicenter of that earthquake. So this is what a modeler would use to model how seismic waves travel through the earth, and he can visualize that data with his tool. In his web application, there's a set of sliders to adjust the transparency and cutoff values and color maps for this visualization. And then just a wide assortment of 3D perspective views in his web application. So, and the reason a geologist wants to use our the X3D tools in this generic coordinates transformation is that we can visualize these kind of data, which in a layered approach is underneath these wonderful map tile images of the Earth that we see. So now I'm gonna risk showing some actual interactive plots from my work in the ocean. And so I'll start with where my institution is about 300 miles north of this in Monterey Bay, California. And where I work, we build robots to measure properties in the ocean. We're real interested in the life in the ocean and measuring things like chlorophyll and taking water samples, looking at the DNA that we can detect in the water to assess the ecosystem health. We were really interested in measuring biodiversity and doing it cheaply and effectively, but we need to visualize the data. We need to visualize how these robots are doing the work. So this is a web application that supports this scientific research. In the application, there's a spatial section and a temporal section. This is just showing some data from one of these robots that dives down into the ocean, collects chlorophyll data, and comes back up. These bright green spots are where there's more plant life near the surface where the sun shines. And then the track here, they were doing a little circle here, a couple of these autonomous underwater vehicles. And hidden here in the spatial section is a 3D tab that gives us a view into looking at what these robots were doing. So one of the features that in oceanography we need to do is look at this upper thin layer of the ocean where all the life exists. And that's a real thin layer, and we need to expand that layer. And a typical trick that oceanographers use is to do vertical exaggeration. So I've exaggerated the vertical dimension here by a factor of 10, which means that the bathymetry in Monterey Bay is much more dramatic than it really is. It actually is quite dramatic. It's about the same depth as the Grand Canyon. It's about a mile deep between Monterey and Santa Cruz here. So the scientists can just go to a website, bring this up. This is actually a public website that I'm visiting here. It's available for you to look at, and we can display any of the data here, navigate around, and look at that. One of the features that we get with the X3D standard, and it's something that Andreas used in his plot, is we cooperate with other domains, like medical visualization has lots of CAT scan data. So the medical community within it, supporting the X3D standard, has developed some volume visualization tools. So Andreas used the same volume visualization used to look at CAT scan data to look at his sound velocity profile data. Another thing that we have is the full interactivity, just using basic web standards with some JavaScript hooks to introduce animation. So now I've hit the play button on this, and now my little autonomous underwater vehicles are playing back, and they're swimming back through the ocean. So the scientists can look at the data this way. How much time do I have, Teresa? I get 5 more minutes, okay. Okay, so then I can show this this one last thing. So this application was designed primarily for these kind of data to look at our robots, but it's really general purpose. Any data that has time series of latitude, longitude, depth values can be put into the system and played back. There was an idea that one of our geologists had to measure these submarine currents that occur in the ocean. Think of underwater avalanches. The scientific term that geologists call them are turbidity currents. And so we invented this thing called a smart boulder, which is the same IMU, the same international measuring unit that you have on your cell phone can tell which way is up. We put that in a pressure housing, and we built these devices that can measure these submarine currents. And the reason we want to do that is, here's a picture that's kind of hard to see, but there's a equipment platform that was completely destroyed by this avalanche of sand that came down the submarine canyon and destroyed it. So we know very little about these things. In fact, until we built these small boulders, nobody's ever measured one of these turbidity currents in situ. So this is one of our web articles. So what these look like, they look like big medicine balls that we can put down into the submarine canyon. Here's a picture of one taken by our remotely operated vehicle, just sitting on the sediment on the seafloor. So we'll put them down there, and they'll sit and wait for them to start moving, and then they start recording the data. And the only hope was that we could at least record the start and end time of these events, because once they would move, they would be buried by the sand. So we had to put an acoustic modem in to then transfer the data afterwards. And then I said, well, we can get a lot more than just a start and an end time. We can actually understand the rotation of these boulders as they're going down the canyon. So I put those data into the same system, and now here's the actual recorded value of one of these benthic event detectors that we call them, that's spinning around. This is actual recorded data. And for me, it was a computer graphics challenge. I had to understand the quaternions that were recorded on this thing. And this big red vector is the axis about which these things are spinning. And the geologist came up with a hypothesis that the nature of the motion changes after the second event. You know, these things would go down the canyon about 200 meters and then wait for 2 months, and then another avalanche would happen, and they'd go down another 500 meters. And he said, well, maybe the second time it's going down, it's buried in so much sand, it's not going to spin so much. So because of the graphics visualization capability we have here and just putting the data into X3D Geospatial, available on a website that he could just use, it was pretty straightforward for him to explore that hypothesis. And this time series here, let's see. So yeah, one of the things he did was to look at the data at this component of data, and it's kind of, I kind of like this plot. It's just a simple XYZ coordinate, but it's the trace of that red vector through space. And you can look at that, and he's made a whole series of plots of what the character of that rotation of the bed is. So this is kind of an unexpected feature, but just dealing with the geographic data in an abstract way that plugs into this wonderful X3D standard that allows us to easily build websites to look at the data in lots of different ways. You saw the geology example, and here's the oceanography example. So, so that's kind of.
Yeah, Mike's spot on.
Oh.
Take questions. Anybody have any questions?
Yeah.
So X3D is the standard for the data format, right? Am I getting that correct?
X3D, it's a standard. It's an ISO standard for, I don't know what's the right way to put it, for representation of any matter of three-dimensional data on the web, and it's designed to deliver data to the web.
Okay, and what libraries did you use to draw this that uses that data?
Right, so I'm using the same JavaScript library that Andreas is using, X3DOM,
Okay.
but there's others that adhere to the standard to some some better than others. Excite is another library, but there's a host of other libraries and tools that support X3D. So we're not limited to just one software package, which is important in the scientific reproducibility world where I live, where I need to have software and be able to make sure that the models I make, like this is that blue thing spinning around came out of our CAD system. So there's a CAD working group and you know, part of the X3D standard. So I can merge all of these different domains and to visualize what I need to visualize. And since it is a standard, I'm assured that 10 years from now that probably there will be somebody will have a software that will help me do that. And I've been doing this for 20 years, and it's been a good thing. Yeah. Yeah. So, yeah.
This is a silly question. The tumble visualization that you have, is that based on the original placement of the benthic event detector, or is it based on some, like what's the reference used for the start of the tumble?
Oh, like the geographic location?
It's on the bottom of this page, this ball of rotation.
Right.
Where does it start from?
We know where it starts because we go down with our remotely operated vehicle and we got an accurate navigation fix for that. But the positions following that are the best estimate from a pressure sensor on there, and then it's called the Thalweg profile, the depth along the bottom of the canyon. So that after the start, we just kind of make a guess where it's going. It's a real challenge because the canyon changes shape. After each of these events, there's new sand waves and boundaries, and it's been a difficult thing to do, but it's so much more information than the geologists have had before to understand these features. So. Okay.
Nicholas, you know, I just want to make sure I phrase something. These people have been doing this work a long time, so they make it look easy.
Okay, no worries at all. Thank you. Well, yeah, good afternoon, everyone. It's a treat to be with you here. My name is Nicholas Paulus, and I'm a faculty member at Virginia Tech. I run our Visionarium lab. And I wanted to, it sounds like maybe introduce a little bit about the Web3D Consortium and the standard that you've been hearing about, Extensible 3D, which is an ISO IEC standard. And what that means is that it's gone through national bodies all around the world to vet it through a process that's multi-stage reviews, and what we get out of that is the confidence for a data-centric strategy. And I'll bring that back up again when I talk about why Virginia Tech is using X3D and what we're getting in terms of successes from that data-centric strategy. You know, Mike was talking about reproducibility, and that's really who are members of this not-for-profit consortium. So it is a 501c6 not-for-profit consortium, now over a decade and a half old, and it's really driven by community members who value their data, and that's what they want to invest in. And so Mike showing some great scientific examples, and I'm going to show some other ones about the benefits of standards, and once you start to take that sustainable look at how you want to store, publish, mash up your data, all the great things that can come out of that. And so there is a good story for Virginia Tech's participation. But Web3D.org, as Mike mentioned, has several working groups. He's being very modest because he's the chair of our geospatial working group. He also mentioned medical, where we're innovating on health records and volume visualization. We have a design printing scanning group, which is tackling all kinds of point cloud issues and 3D printing, which I'll show some examples there as well. All of this really brought together by the X3D SIGGRAPH, which can be encoded in all different ways, can be manipulated by lots of different languages. And so it's a really a suite of standards. This picture here is from my cave at Virginia Tech. We are able to run that same scene on a mobile phone, a laptop, a 27 million pixel projection system, a multi-touch screen. We didn't recompile anything, we didn't change anything. It's the data that's important, and we start to be able to then deliver that data and bring from all different kinds of sources. And it's pretty exciting. I mean, once you're on the web, there's a lot of fun things, being able to integrate with services like an online web service. But lat long and the X3D, the rendering coordinate system, that's really kind of the sweet spot, as Mike mentioned, for these standards. And you can have part structures and all sorts of things with this scene graph. When I began, so web3d.org, please come and visit, join. We do have a public mailing list about the X3D spec. You're welcome to join that. And in fact, Mike mentioned several of the open source tools. This is the other thing, is that there's dozens of X3D compliant importers and exporters and all kinds of great tools. And so being able to get that greatest common denominator of my data and put it together in different kinds of contexts, this is really valuable. And so this is why Virginia Tech works in this space. So we've been here in this CartoBOF maybe a few years ago and presented 3D Blacksburg. And 3D Blacksburg is a multidisciplinary, interdisciplinary collective. We're pulling together data sources from all kinds of places. So we're looking at, national elevation. We're bringing in stream centerline data from our state. We've got the campus building models, the town GIS models, right? We've got, here's some SketchUp that our architecture students did. All put into, again, from all these different sources, being able to build context. And of course, having our typical grouping types of functionality to add or remove different layers. So 3D Blacksburg sort of set us up a long time ago. The idea was we want to be able to, whether it's QGIS or a photosphere from someone's data 360, we need a spatial data infrastructure. And so with our Center for Geospatial Information Technology, we started to build 3D Blacksburg. And it's really had a lot of benefits. So I'll close this one and kind of bring up a master's student. So here's, again, someone who was not in graphics, again, a domain expert, wanted to redesign the alleyway behind one of the blocks of Blacksburg. And of course, density of development is a hot topic if you're in zoning meetings. And so this design really let the whole group see what the environment was like. And I'll give it a little fly here. Oh, is it going? Oh, yeah, okay. Let's see. So again, bringing this SketchUp model, which is the design of this walkway, pedestrian walkway, and being able to put it into the context of the rest of the town. All right, so she's made little plazas here. These are large buildings. We're trying to do dense, denser development, so we're avoiding sprawl. But here's a master's thesis there. She could bring this data into 3D Blacksburg very easily. And kind of the nice thing about this was that once we had it to X3D, there's all kinds of other stuff we could do with it. So that's what I'll get into now. I mentioned our Visionarium Lab cave. So this is an immersive projection room. We're in our third iteration, so we're at about like 26.5 million stereo pixels with head tracking, and we were able to bring in the town planners, the neighborhood leaders, all into this model and put them on the curb, right, in the cave. And so it's a projection environment, so they can see each other, they can see what they're pointing at. It's at human scale. And this was the subject of her thesis. You can look it up. It turns out there's a very strong benefit for doing this kind of immersive design and planning. And she measured that and documented it. But again, it was a design project that got then mapped into a geospatial context and then got put into virtual reality for a real task. And so that's what X3D let us do in this case. I'll talk about another example. So once we were able to bring this kind of geospatial data into virtual reality, for example, X3D, we actually started to work with the National Park Service and the Appalachian Trail Conservancy. And we basically took maps of the trail. What they're really interested in, of course, is preserving the view sheds and, let's go maximum, and historic significance, the natural heritage of these areas. So here's an example from a certain section of trail where we're crossing the New River. And you can see we have maybe 1 or 2 levels of detail in terms of the imagery. But we've pulled out, the markers from, I guess this is probably Esri in the back end. And we're taking the symbology right out of there, no special thing involved. But what they're trying to do is to understand how they can document these sites along the trail. And so one example of that might be this application. Let's see, it's right over here. Yeah. So again, bringing in lots of different kinds of data. Here's a certain plot down at the foothills. Let's kind of zoom in here. And I mentioned, these 360 photospheres. These are really, really exciting, mostly because lots of people can make them, and it's becoming easier and easier. So, but this application, basically, we just went around the site and captured, right, with a handheld laser scanner. Here's the mushroom logs. This is the right way to grow shiitakes, by the way. And put them, of course, in the photosphere. So you get this, again, the object, the context, and this really nice ability to do mashups. I'm looking for this one. Here's Professor Munsell. He's counting his ramps. He's got a GPS location, and this is the scan we took of him in the site. One more kind of fun one. This is, well, actually 2 more. So we're thinking about VR. I've been looking at projection environments and showing you those. But we also did one with the USGS. This is a project where we've basically made a citizen science application to try to understand, can people help us, assess the health of trout populations in our streams, right? We have a real problem with acid rain still, and our populations are challenged. So we basically made a quiz. This will be published later this year in the fisheries community, but delivering in a VR mode to from these underwater cameras to schools and K-12 context. So we're getting students into Google Cardboard, Oculus Go's, and they're going in and counting, right, the fish. And then, of course, the scientists are measuring the sensitivity of observations compared to the ground truth. They've actually gone in and shocked these pools. But nice. Yeah, stick it right here in your web browser. There's a VR. And all of a sudden, we've got, from 34 different states, 4,000, I think, observations in so far. Great. Okay, so the last one, thinking about the ways that we get to use X3D for, again, some success stories. From the medical community, the NIH 3D Print Exchange started to publish a huge repository of stuff in X3D. And the printer companies took notice. They started to get some native support. And so once we have, for example, 3D Blacksburg, maybe we 3D print it, okay? And here we're actually overlaying like a sand table style projector of all of the accidents. So we just won a national state governor's award. I'll loop this. For this project, digitizing crash events. There's several hundred million, of course, in the state. And so you can see the dangerous intersections here on the side of our campus. And this, again, is the power of having that one platform, and all of a sudden with that data-centric strategy, we can play well with others, we can move our data between tools. And so I hope that you'll come and find the Web3D Consortium. We have a booth this year again, and talk with us and join the fun. Thank you. I think we're 9:30. Thank you. Yeah.
Sorry, I'm seeing a lot of convergence between the general city communities and more scientific engineering. How do you see like that moving forward for off-formats? Because it seems like USD things like Pixar environment, a lot of formats of the engineering medical communities, but then someone you get people who are trying to integrate that into a game engine. How do you see that kind of convergence?
Yeah, that's a really tough question. It's the $100 million question, really. As you can see, you know, there's lots of demand and need for this data to work together. And one way of looking at it was, well, the market will sort it out. Meanwhile, all of us content creators are really suffering. That is an issue. So I don't know, to me it's maybe being more vocal about if you have requirements around sustainability of data, and in the procurement process, talking to vendors, making sure like, hey, you know what, this will be really useful, and I'm gonna need it 10 years from now. Please support this format. The other way is that I'm slow going, but I think it's showing positive results, is going into those standards meetings and just engaging, right, with the people who are here in this room and being like, okay, you know what, we have a process, we know we need to get these requirements out, and so it's not gonna be a Highlander scenario, you know, the winner take all, or there can be only one. It's gotta recognize it's an ecosystem, right? And so I hope we can take that forward and really work together more productively for the sake of, for the data.
File format interoperability. Okay, well, everybody at this convention is trying to gut everybody else. Just in case there's old guys who have seen this. So we're having that problem. The only, and there doesn't seem to be too much of a solution because it's expensive, and even the open source community then has trouble.
Yes, indeed. I think there's certainly the fragmentation is an issue. It's, if you think about common denominators, though, even all of those medical conferences and the geospatial conferences, SIGGRAPH is kind of where we're trying to play this out. So I look forward to talking with you. Thanks again.
Hey, so a long time ago, people asked that ESRI come here, and it's been my pleasure. They've come here, how many years? 5 or 6 years. So ESRI is here to present some of their stuff.
Thank you.
Introduce more.
I'll introduce myself and my colleague as well. All right, so my name is Tamara Belina. I'm a senior software engineer with Esri, and as Teresa said, we've been here the last 4 or 5 years. I think I presented the last 3 or 4, forgot. But yeah, we've been coming to here, and along with me here, Tobias Mansfield Williams is gonna also co-present. We'll talk about the 3D GIS in general and the ArcGIS platform, and we'll touch different aspects of our software, and we'll also show you some live demonstration. And if I have time, I would also like to show you some demo running on the mobile device as well. So let's just get on to it. So I've shown this slide in the past years, and I keep showing it because it's true, which is the future of GIS is immersive, it's visually compelling, and it's temporally aware and user-friendly, enabling us to create all this new environment for analysis and new user experiences. So It was true 2-3 years ago, and it's still true, and it's changing, and that's the message that we wanted to drive. Now, users are not just asking for 3D just because it looks cool. You know, I want to show my map on 3D now because that's the thing to do. But it's because you can get more accurate representation out of a 3D representation. We live in a 3D world. Our representation should be, you know, in 3D. You can communicate with non-technical users or stakeholders much easier with 3D than with 2D maps. And you can also visualize features that don't exist or that don't look apparent in a 2D map that will just pop out at you in a 3D world. Now I'm going to just cut to the chase because we have very limited time and we have 2 presenters here. I'll just go through the things that we've been working on this year and highlight some of the areas. So 3D in 2018 and 19 has seen huge growth. And one of the area that has been actually a monumental shift or change in our opinion is BIM and AEC. With our partnership last year was Autodesk actually. Now our flagship desktop product, ArcGIS Pro, being able to read Revit files directly and process them, and being able to share that as a 3D scene layer has been a huge, huge boost for our users and for the community as a whole, we hope. In areas of interactive tools, we've added interactive capability throughout the platform, rolled out in the different application, ArcGIS Pro, ArcGIS ERS, as well as City Engine. And this new interactive tools will be continually added into the different products that we have. Both the Seam Viewer, this is our web-based viewer, and ArcGIS ERS, which is available for free and as a desktop product as well as a mobile product, are now capable to search content associated with feature attributes. We've added the new experiences for underground and modeling and navigation also throughout the products and application. One new product that we introduced, actually 2, one in the working, ArcGIS Urban. This is a planning-based scenario application that allows you to integrate urban scenarios. Is also a new offering from us. In the areas of content, lots of new content has been added in the ArcGIS, in the Esri Living Atlas. One example of that is the global terrain data from Airbus. This is best of the class elevation data available that you can use for free within your applications. And partnership with various data providers, including Nearmap, Vricon, that now generate integrated mesh content or I3S content. Means that you can get provision mesh for anywhere, as Caesium showed earlier in Egypt. You can get content almost anywhere. And this ability to get content cheaply has really dramatically changed the whole GIS scenario. And things that used to cost hundreds of thousands of dollars are now much, much, much cheaper. And you can actually acquire this data faster, more frequency, and with better resolution. So what really ties it all together is our solution for streaming massive amounts of mesh data. It's called I3S, Index 3D Scene Layers. I3S supports the storage and transmission of massive amounts of 3D objects, as well as 3D objects with attributes, as well as integrated meshes that cover millions of square miles. It was designed from the ground up to be cloud and web friendly, as well as being based on JSON and REST standards. Mike earlier talked about the coordinate systems and the vertical coordinates being essential for any 3D system. And I3S from the get-go, from original design, supported multiple coordinate system, including vertical coordinate system, which is, a lot of times we take it for granted, but it becomes a real problem. We had some data providers that were providing data that were 30 meters off in Europe, and people are not happy, So those things are really important, and people need to pay attention to the coordinate system, including vertical, when they publish their data. And I3S allows you to specify that. A key point about I3S is this organization of, and I tried to mention that earlier, this organization of geospatial data using a bounding volume hierarchical structure and tiling the data into this node-based spatial indexes is common to all the different layers that are supported within it. This is very common now in the industry. There are different formats that allow you to do that, and I3S is one of them. I3S is free. Anybody can author I3S content, generate content, read content, as well as propose changes to the standard or specification. In the fall of 2017, I3S was one of the first streaming solution for streaming massive amount of geospatial content that was adopted by OGC. Not only that it was adopted by OGC, but it's already evolving. A standard is good for sharing, between different applications, but that does not necessarily mean that it needs to be static. So I3S has evolved already since its adoption in 2017, and right now, currently, there are 3-layer types that are supported in I3S. 3D object, integrated mesh, and point are supported or part of the OGC 1.0 standard for I3S. Currently, we're going through the OGC process of adapting point clouds, augmenting the current I3S standard and specification. But as I said, it's a living, breathing document or specification, so it still continues to grow as we put a lot of effort and energy into maintaining and updating this. And I3S also introduced a building scene layer that allows you to visualize massive amounts of, this is the innovation and movement that I mentioned in the BIM and AEC world happening now. So let's take a quick look at the different layer types. 3D objects, massive amounts of 3D objects for capturing cityscapes with millions and millions of textured 3D objects. And you can stream this content to your 3D desktop and web application. Similar to 3D objects, but without the mesh segmentation information, typically is a layer type that we call integrated mesh. This is skin of the earth type of layer that captures buildings, trees, and cars and whatnot. And this is the one that I was mentioning that is so much cheap and easier to collect these days. So that's the second layer type supported in I3S. Third one is, which is now in the process of adoption, is a point cloud. Point cloud, billions and billions of points of data that either have RGB content or classification are also layer type that are supported in I3S. All these 3 layers share the same bounding volume hierarchy, principal selection criteria, and ability to stream across the web. I don't know if you missed it, but if you look back, you'll see this. This is a concept video or idea for building scene layer. So imagine that you have a city. The city that you're seeing, it zooms out, you'll see is San Francisco. This is hundreds of thousands of buildings, highly textured 3D object layers. But imagine now, on top of one of the buildings, there's the same building on top of it. So when I zoom in, you will see what you see is the city of San Francisco on top of that building. So the idea being here is that building scene layer, or BIM or AEC in that kind of context, brings this much scale. We have your exterior of your building, but then when you delve into the building, you actually want to be able to see the rivets here and the knobs and the phones and whatnot. So that's why we want to show this video that that's the kind of scale that we work with when you're working with building scene layer. But not only that, you want to visualize in this huge amount of scale range, but also you want to be able to peel it through, swipe it through and be able to reveal the content of a building scene layer. So here's a typical building, you are seeing different layers or different representation of the same data, the same content with the single layer. Tobias will show us a live demo of one of these videos that I'm showing right now. So moving on. Some numbers to throw out at you here. Take a look at the third image in there, point cloud, 638 billion points. This is the Netherlands HN1 and HN3 survey. And this is massive, massive amount of data streamed to your desktop, mobile application over the web. Textured buildings, same as the one that I showed in San Francisco, 80,000 buildings, high resolution data, and so on and so forth. It continues with point cloud as well as 3D building objects. I3S and AI, we've been investing and working a lot in AI and deep learning. One of the areas being able to recognize meshes, segment meshes automatically. So most of the mesh data that you saw earlier, they come without any segmentation or without any attribute information associated with them, which makes them a little bit difficult to work with. So AI and deep learning has been an area that we've been interested to, segment meshes and point cloud to be able to classify them. Different data providers that are generating I3S content now, from Vricon, Nearmap, and Bentley. All of those folks are generating I3S content for usage. I will quickly skip through the different platforms. ArcGIS Pro is our premier desktop application that allows you to author, publish, consume this system. And then moving on, the Scene Viewer is the web application that allows you to consume the same kind of content. So across the platform, when we offer a solution, we try to make sure that it is consumable across the platform, desktop, web, mobile. And then lastly, the ArcGIS Earth is also a free downloadable application that runs on desktop and mobile systems. I think I have one more last video in here, and then I'll pass it on to Tobias. ArcGIS Indoors is a new offering that we have from Esri that allows you to actually visualize interior spaces. And then here we are SIGGRAPH. So this is more relevant to people here. So GIS has been expanding in the game engines world as well. So City Engine, our desktop application with Unreal Engine and Datasmith, has been really powerful in offering this. So I'll let you watch this video, and then I'll maybe pass it over to Tobias. The idea with this video is that, in a VR world, yeah, you can sit around a desktop and work, but how about, you are able to communicate information, virtually, sitting in a virtual table, looking at a virtual window, and being able to not only model, but visualize different scenarios. So this is a city, you have different buildings, and you'll be able to see shadows as well as different scenarios when you're switching through the slider, virtual slider again. So this is GIS now. I mean, and that's why I keep showing the first video, the first slide all the time, is that it is evolving, it is changing. It's not your grandfather's GIS anymore. And that was the point that I wanted to communicate. So I will just exit the slides here. How am I doing for a video? I'm okay?
Yeah, about
5 minutes? Okay. I want to bring in Tobias because we've got 6 minutes or so, right? Yeah. So let me bring on Tobias, and if we have more time later on, I can. All right.
Oops, sorry. Okay, so hi. I'm a developer on Twice. I'm a developer on the Esri JavaScript API. I work in our R&D center in Zurich, Switzerland. I'm going to show you some of the new features in the Scene Viewer and the JavaScript API. So to give you some context, this is ArcGIS Scene Viewer on the right side. It's an app that users can use to author and view scenes without programming, and it's powered by our JavaScript API, which is more of a developer-focused thing, which is free. It's an API that developers use to create their own custom 3D mapping applications. So Tamrat talked about BIM across the platform. And on the web, we now support building scene layers. So this is an example of a building scene layer in the Scene Viewer. As he briefly showed, As he briefly showed, you can go in and you can use this building explorer to
hide, for example, the facade elements. So now we can see the interior. The resolution isn't great. You can filter by floor. And this is all data that's been extracted or exported from the BIM model. It's not been authored in the scene viewer. An alternative way of exploring a building is using the slice tool. So the slice tool is built into the scene viewer, and you just click and drag, and it reveals the interior. It's got these handles to adjust. And for example, if we want to view this flight of stairs in the context of the cross-section, we can exclude it from the slice, and now we see where it is. And we might want to then make a measurement while the slice is active. So that was building scene layer. I'm going to show you another new feature in the 3D JavaScript API, which is sketching. And it's what it sounds like. It's you can sketch polygons, lines, points. So for example here, this is a demo app demonstrating a possible planning workflow. So we can draw polygons with extruded symbology to mimic buildings, and we might want to, if we don't like this, we can edit it. We can also place, with also the Sketch API, we can place models on point geometry. So this is a library of Esri provided models. So we can place a construction crane here, and we can click on it, and we get these handles. These can be used to scale, rotate, and place the model. And these handles are built into the API. They're not a custom thing for this app. And this model is actually a GLTF model, and that's another new feature, is GLTF support. Not limited to Esri models, but here we have, for example, an integration with Sketchfab, and we can search for something appropriate for the coast and import this, and now it's using the GLTF import capabilities of the JavaScript API. And in the same way, we can place it somewhere. So now I'll quickly talk about the new features relating to smart mapping. And smart mapping is what we call 3 minutes. Yeah, that's good. Smart mapping is what we call the mapping of attributes on graphics to color and size on the symbology. So let me just open these in the background. So this is line feature data of a storm drain network in Redlands. And for example, we might want to visualize the age of the storm drains. So we can map the installation year to the color and make it a bit clearer for the dark background. Oops. And now if I you can kind of see behind the legend here that the light lines are newer pipes, and the older ones are in darker colors. Using the same data, we can also visualize it with 3D symbology. This is in scene viewer, we just select the 3D style, and we can take a closer view and go in and customize symbology, maybe give it a more distinctive color, place it underground, and give it a square profile. Similar to line smart mapping, we have polygon smart mapping as a new feature. So these are building footprints of buildings in Paradise, California. Paradise was recently affected by quite a bad wildfire. This is a data set that includes some classification of the damage. So we just select the damage attribute, and we can see that, so red is destroyed, so it was really a bad event, and yeah, some of the buildings survived. And for a more realistic visualization, we can extrude the buildings by their height. And finally, I'd like to show water styles. So this is a scene of the River Spree in Berlin. If we take a closer look at the river, it's just a simple plain polygon. If we go in and we configure the layer in the scene viewer, we have this new water style. We select it, and you can see there's now a reflection. If we take an even closer look, there's a nice animation as well. And we can configure this water now. We can give it a lighter color maybe, or we can change the characteristics using these pre-prepared types, so ocean and ocean, bigger waves and so on. Yeah, so these are some of the new features in the JS API and Scene Viewer. If you're interested in technical details or how to use them, come and speak to me. And this presentation, or these slides that I showed you, are available at this URL here.
Hold that. People can see this URL.
Yeah.
Do you guys have a booth here? Or?
Yeah, we've got an exhibition.
We do have a booth. I'm not sure the booth number. Anybody from Esri here that knows the booth number? Yeah. Oh. But we do have a booth. You can't miss us. We're down there.
I don't have time for these guys to do questions, so
Yep.
come and talk to them. We'll talk to them afterwards. I'm sensitive to it. I just want to make
You
sure.
can ask us after. Sorry, we ran a little bit over.
No, you did great, but we just got to get an Uber on here.
All right.
It's my pleasure.
First time Uber has ever been here before, so I wanted to give them 20 minutes. Go for it.
Thank you.
Sure. I'm going to take your seat. You want to introduce yourself to my apologies.
Oh, it's fine. I can introduce myself.
Thank you.
Oh, sorry. Wait a second. Oh, what is this? Sorry, 1 second. I just need to set up the prison. Hello, everyone. My name is Xintong Xia. I'm a software engineer in Uber's data visualization team. Today, I'm going to talk about the open source, the geospatial visualization frameworks from our team and how these frameworks solve the real-world problem in an informative and performant way. So as the data visualization team inside Uber, our mission is to create these visual solutions for our engineers, data analysis, scientists, operations to explore the variety of data and get insights from there. And maybe the engineers want to know how the business metrics after they roll out some experimental features, or our autonomous team may be interested in how their decision system or their models perform through their vehicle logs. So here our team came to help and create these different kind of web applications. So beyond these internal applications, our team also have made a strong commitment to open source and open standards. Most of the frameworks in our team have been already open sourced, which I will cover more detail in the following slides. One of the biggest or well-received project from our team is Gl, which is a data agnostic and highly performant web application for large-scale data exploration. And now this project is moved to the Urban Computing Foundation as its first hosted project. And another application recently open sourced is Uber Movement, which share the dynamic insights about the traffic and the mobility of the big cities where Uber operates, help the urban planners or government to better understand their city. And so you can say our team is heavily involved in the different communities, Urban Computing Foundation, WebGL, and 3D Tile, GLTF, and so on. So after years collaborating both internally and outside Uber, and the efforts put into the WebGL-based frameworks, our team really helped build up these entire suite of open source geospatial visualization frameworks. So it's from the WebGL-based component library to basemap to the rendering framework, editing and analyzing frameworks. Our team provides a variety of different kind of web-based applications, which means with these frameworks, you can basically render on any kind of computers as long as the browser supports the WebGL. So here is a hierarchical representation of all the frameworks inside our team. So it really have provide the very complete and comprehensive libraries. From the very fundamental math operations, Mercator projection, decoding and encoding data, to the large data set focused rendering framework like DuckGL and our basemap library, RedMapGL. Also, we have further provide these different kind of applications. So most of our framework here are in JavaScript, but big efforts we have devoted recently is the PyDeck, which is a set of Python bindings make the spatial visualization available on top of the DuckGL, which also actually integrate with the Jupyter Notebook. As I personally think is very useful for the data scientists or people who are very familiar with Python or Jupyter Notebook. So in the following part, I'm going to introduce the three products from our team. The first one is the DuckGL. This is a WebGL-powered, GPU-accelerated, and widely supported framework, which can render the large amount of data set very performantly and interactively. So with the DuckGL library, you can get more than 30 layers for free. We're not just providing the primitive layer like a scatter plot or line layer or bitmap layer. We also have the more advanced layer catalogs. For example, the mesh layers, which you can render your GLTF SIGGRAPHs in a very for many points. We also have the different geospatial indexing system, for example, Google's S2 and Uber's H3 layers. And our API actually designed very easy to extend it from, which means you can create your own customer layers on top of DuckGL. So here is an example using DuckGL's arc layer to render United States country migration. DuckGL actually provides a very unique geographic filtering function, brushing. With this technique, you can actually filtering or highlighting these arcs by just moving your mouse positions, and all these destinations connecting to this to your mouse position will be highlighted. So this is another example showing the highway accidents in the United States. And we use the two sets of colors to indicate the fidelity levels per 1,000 miles. And you can say DuckGL layer can interpolate these colors for more than 400,000 vertices very smoothly. And also we have introduced another dimension year. And these fidelity actually can change smoothly as the year changes. And this is another demo which I personally think is pretty cool, because we kind of divide this entire screen into 4.5 million gray cells. And whenever the user interacts with this map, you either zoom in or out or panning the map, our DuckGL layer can just recount all these points fall into each gray cell and re-render it. This can only be achieved by leveraging the parallel computing power of GPU. So for now, we have seen the rendering power of our DuckGL layers. Another appealing feature about our framework is it can integrate with different kind of base maps. We have been collaborating and partner with the Mapbox for a long time, and we also have the RedMapGL library, which is on top of Mapbox. So DuckGL can seamlessly used with the Mapbox base map. And in the most recent Google I/O, it announced the collaboration with our team, and we have provided the Google Map module inside the DuckGL. Also, we started collaborating with Caesium to develop a 3D tile layer and a new tiling system that can load the data progressively, which enable the DuckGL to handle much more point cloud data. We also have the internal tile layer, which can parse and render the two-dimension tile. So here is DuckGL's scatter plot layer on top of a Google map. I believe in this picture shows the tray layout in Paris. And another example using the tile layer serving OpenStreetMap raster tiles dynamically based on your current viewport zoom level. So the second product I'll introduce here is KeplerGL, which I already briefly talked earlier in the earlier slides. KeplerGL is a data agnostic, high-performed web application which can be used for visual exploration of the large-scale geospatial data sets. Since DuckGL is built on top of the DuckGL, it can take the full rendering power of the DuckGL and the GPU rendering power. So this project is moved to the Urban Computing Foundation already. So let's take a closer look of how KeplerGL can be used to explore the data. Yeah, it's not from beginning. Kepler, one of the biggest feature about KeplerGL is you can actually upload your data from your local file, if it is in CSV format or GeoJSON format, and the KeplerGL can just interpret your data based on your file format, and then you can choose the whatever layer you want to represent your data. Here in the demo is showing the San Francisco contours. Yeah, here it is. By just drag and drop your file from your local laptop, and Kepler can automatically render it. So, and another big feature about Kepler Gl is it's highly customizable, which means you can choose whatever the color, styling, or length or width of your layer, and create a very professional rendering or visualization map. So here is another example about Kepler Gl. So Kepler Gl is not just about rendering a beautiful visualization on top of base map. It can also further process your data. This demo shows like the LA trips and aggregated into hex bins. So by changing the radius of your hex bin, Kepler Gl is able to recount all these trips fall into each small hex bins and re-render it very smoothly. So again, you would say Kepler Gl doesn't need you to, doesn't even need you to code or do a very complex data processing. It's totally client-side and very easy to use. So the third product I'll cover today is Scape Gl, which is just released February of this year. This is a rendering framework for autonomous vehicle system. It can render the vehicle logs, help the people inspect, explore their logs, and get insights from there. And also on top of DeckGL, which means it can render your log in a performant way. So here is a short demo. Here is a short demo for our Streetscape framework. From here, you can say there's an autonomous vehicle running on top of a base map, and surrounded there are a bunch of bounding blocks which represent the other vehicles and pedestrians. All these bounding blocks and vehicle refresh many times a second as the play moving forward. Also, not just about this 3D rendering thing, you can also have the 2D charts on the left panel and the video player on the top right and the playback control component at the bottom from this Streetscape GL library. So these different components serve as a very comprehensive and end-to-end user experience. Yeah, so that is the end of my presentation today. Our team is a group of people who are very passionate about the data visualization and the WebGL. We would like to apply these technologies to create more beautiful visualization and get more insights from the data. So if you're interested in our work, you can reach out or check our website. All these frameworks I mentioned earlier is open sourced. You can just search it by its name and all available online. Thank you.
Anybody want to ask a question?
Yeah.
Yeah, very, very impressive.
Thank you.
If I ever want to visualize my robot data in the ocean, what would I have to do with my data sets to use these JavaScript toolkits? Would I have to put them behind some specific kinds of web services, or how does that work?
Oh, is your robotic data you want like moving or static?
So just like the last demo that you showed of the
you need to
driving.
moving.
If I have data that's similar, what do I have to do to my data to get it into your visualization?
Yeah, it's actually, I'm not sure our framework can deal with the ocean because we designed for the moving on the ground, but I'm not sure at that part. But we have this,
So
yeah.
time my robot's job to Uber drivers.
So we have this library called Scape Gl, and it does require some coding, and we have the modules inside. Sorry, not modules. Anyway, we have a playground. Oh yeah, here we have a playground app which you can download and just. I believe you can install the package and run the command like just like Young Start, and you can basically load your local data from there and visualize like the demo I just showed. And yeah, it's basically your data don't need to be serving as an application. You can load your local data. Yeah.
Okay. Thank you.
Yeah, thank you.
I can take one question maybe. We're at the end of the rope, but really, one question.
What was the difference between Kepler GL and Vet GL? Like one which you want to use one versus the other?
I would say the Kepler GL provide more the data analyzing functionality on the fly. And another difference is Kepler GL doesn't require coding. But if you want to use DAGL as a rendering layer, you still need to do some code by yourself. Yeah. Yeah, I think this is in there.
Take yours, make sure you get it here. That's yours. Okay. Okay, everybody, it was a great Cartograph. This is it. We hope you come back next year. Thank you for all the presenters. Thanks, everyone. We hope you enjoyed it. I think we covered a lot of territory here. Very informative. Okay.